All right, so a big part of looking at multi-electron atoms is understanding this idea of electron-electron repulsion and something called electron shielding. So we're going to look at how we can fill orbitals in an atom, um, and how that relates to, and also kind of the periodic table properties are all going to be, you have to understand this idea of electron shielding. So electron shielding it's kind of like if I were to ask you a question and say why, if you just said electron shielding, you're probably going to be right 50% of the time because it is such an integral part of the properties of which we find for atoms. So the number of protons defines the atom, but how the electrons are arranged in these atomic orbitals really explain a lot of its properties and then interactions with other things. So um, if we just kind of explain this a little bit, um, we have orbitals in which electrons are closer to the nucleus, have lower energies because there's higher attraction because they're closer to the positive nucleus and experience less electron shielding. Okay, and so what that means is that it is harder to remove electrons closer to the nucleus because there's a stronger attraction. Okay, so in a multi-electron atom, which again is everything except for hydrogen or one electron atoms. And so the idea is that if we have, well, we can put it this way, that the, let's see, we're going to call this electron shielding. The idea here is that if we have a positive nucleus, and again, we're going to kind of use this Bohr model of the atom for this particular representation, or we can just, not do the orbitals, but with the positive nucleus right here, we have two electrons, electron 1 and electron 2. Okay, now we're just saying they're on average farther away from the nucleus. So if we draw the attractive forces in green, so we have the attractive force here, so between the positive nucleus, and we also have an attractive force. It's smaller because you can see that R is going to be greater. So this is, if we call this electron 1 and electron 2, that R2, and this is R1, we know that the, let's do this in black, the electrostatic, if the energy associated with these electrostatic interactions is proportional to the charge of the positive times the charge of the negative divided by R, so that the smaller the R value, the greater the attractive force. And so we see that just because an electron is further away, it's going to have a lower attractive energy. But in addition to that, now we're going to have something called shielding, which is that these two, so we have some repulsion, but we also have that when this electron is trying to quote unquote see the nucleus, it can't because of the interactions, repulsive interactions it has from the proton. And so what we're going to have is we're going to call it something called the effective nuclear charge, which is Z. That's the charge of the nucleus normally, and we're going to say it's the effective nuclear charge, and it's going to represent so this Z effective is equal to what the charge would be the nuclear charge. So this is the nuclear charge. Nuclear charge minus how much the outermost electron, or whatever electron you're referring to, is shielded. So this is called the shielding constant. Shielding constant. Now this shielding constant is going to be dependent on the number of electrons that are in between the electron you're considering and the nucleus. So as you move further away, so this goes up as n increases, because as you go up every n value, your average distance from the nucleus increases. Okay, so that is, to summary, we can summarize that by saying that, so if we have n sub s, n sub p, n sub d, n sub f, that the energy increases, which is another way of saying less attraction to positive nucleus, which I know is kind of weird to think about that. And so we see that just with these within a multi-electron atom, the s orbital is going to be closer than the p, than the d, than the f. And then as n increases, we also see the attraction going down. So we can actually summarize that very nicely in a plot, which we've already done before. This is the, again, probability of finding an electron and distance from the nucleus, same plot we've been using. And now what we're going to do is we're going to plot the 1s, the 2s, and the 2p to understand something about why we bump up energies for the 2s and the 2p, or specifically the 2p. So we've got the 1s. We'll draw that first. This is the 1s. We'll do blue for the 2s. 2s is going to look like bump. This is the 2s. And then the 2p we're going to do in purple. And so remember that we've already drawn the 1s and 2s. We've seen that. But now if we overlay the 2p, remember that the 2p only has one hump. So it kind of comes like this. This is the 2p. Okay. And so we can see a couple things here. We can see that on average, the 2p looks to be closer to the nucleus. But we forget about something. We forget, or we might not notice, that this little hump here. So this little hump, this little hump will shield pretty much all 2p electrons, making the energy of 2p electrons higher than the 2s electrons. Okay, so this is actually really useful. This is very important because we said that when you have multi-electron atoms, we have some interactions that cause the 2p orbitals to be higher in energy than the 2s. The reason why, the explanation that we can provide using this plot is showing that because the 2s has this bump here, that all of these electrons in this bump are going to shield pretty much everything, because almost every the probability of finding a 2p electron, all of them are going to be further away from the nucleus than the electrons in this little bump here, and so we're going to have all the 2p electrons are going to be shielded. So this idea of shielding will make it a higher energy, and that's why we see the 2p higher than the 2s. So that's super useful to think about in terms of electron shielding, and with respect to the energy levels of subshells for the same principal quantum number.